Hello, students, and welcome to today's Friday Math Happy Hour. Today, we're going to cover the Exam 2 review. I'm going to list, here on the right are the list of the topics that I'm going to cover. Graphing exponential functions, which is 4.1. Applications of exponential functions, 4.2. Graphing logarithmic functions, 4.3. Writing exponential equations into logarithmic equations and vice versa, 4.3 also. Expanding and condensing logarithms, also 4.3. Solving exponential and logarithmic equations, 4.4. And chapter 5 are the finance is a finance section. 5.1 is simple interest. 5.2 is compound interest. 5.3 is future value ordinary annuities, and 5.4 present value ordinary annuities, which is 5.4. Okay, now so let's start with graphing exponential functions. Okay. So this is the most basic graph to graph, which is the f of x equals to 2x. The 2 is considered my base. Okay, so when you're going to be graphing exponential functions, the y's values for x are always going to be from -2 to 3 or -2 to 2. In this case, we're going to use -2 to 3. Okay, so let's draw ourselves a little table. We have x and we have f of x. F of x is the same thing as y. Okay, so let's plug in. Right, so when x is -2, here on the right, this is what we're going to do. Okay, this is my original function, so I'm going to evaluate f of -2, which means I'm going to plug in -2 for every x. So 2 to the negative second power will give us 1 over 2 squared, which will be 1/4. So when x is -2, f of x is 1/4. We repeat the process for all the values for x. So now let's do f of -1, which will give us 1 over 2 to the first power, which will give us 1/2. So when x is -1, my y is 1/2. Now let's evaluate at 0. So f of 0 will give us 1. Anything to a 0 power will always be 1, or any base to a 0 power will always be 1. So when x is 0, my y is 1. When x is 1, right, we plug in the 1 for the x, which would be 2 to the first power, which will give us 2. So when x is 1, y is 2. When x is 2, we're going to plug in, evaluate our f of 2. We're going to plug in 2 for the x's. So it's going to give us 4. So when x is 2, my y is 4. And lastly, when x is 3, we evaluate f of 3, which will give us 2 to the third power, will give us 8. Okay, this is the reason why we don't plug in numbers more than 2 or 3. Why? Because if we use 4, right, if we evaluate at 4, it's going to give us 2 to the fourth power, which will give us 16. And 16 really will be off the grid, especially if we use larger numbers like 4, 5, 6, 7, and 8. They're going to be off the grid. So these are the wise x values to choose is from -2 all the way to 2 or perhaps 3. Okay, guys. So now we're going to do our function, right? Our graph. So, for example, right, when x is -2, right, my y value is going to be positive 1/4. So it's right here where the arrow is. And when x is -1, right, it's going to be 1/2, right there where the arrow is. And if we plot all these points, this is a graph that is going to make. It's called an exponential graph. Okay, now, what happens when we have, if they tell you the graph, f of x equals to 2 to the x minus 1? So again, if we plug in values, right, for the x, we're going to use the same values for x, -2, but now we're going to go all the way to 4, because if we plug in 4, 4 minus 1 will give us 3, which would be 2 to the third power will give us 8. So these are the values that I'm going to plug in for x. So again, we repeat the process, right? So when it's -2, it's going to give us 2 to a -3, which will give us 1/8. When x is -1, it's going to give us 2 to the negative second power, which will give us 1/4. So when x is -1, my y is 1/4. Right? Anything to a 0 power, right? But if we plug in 0 here, it's going to be 0 minus 1. So it's going to give us 2 to a negative first power, which will give us 1/2. Now, when we plug in 1, it's going to give us 1 minus 1, right? It's going to be 0, so it's going to be 2 to the 0 power. And any base to the 0 power will always give me 1. So when x is 1, y is 1. Now let's plug in 2. F of 2 will give us 2 raised to the power of 2 minus 1, which will give us 2 to the first power. The answer will be 2. So when x is 2, y is 2. When x is 3, y is going to give us 4. And when x is 4, my y is going to give us 3. So 2 to the third power will give us 8. Let me see what I did here. I don't know what I did here, guys. Let me see here. Oh, here we go. So it's 8. Let me go previous. Okay, now this graph, all these values, right, they're going to shift 1 unit to the right. You see, let me see here. I didn't graph the previous graph. Let me go back real quick. So let me show you how this graph will look like. So because it's in the exponent, the x minus 1, every y value, every value shifts, the x value shifts 1 unit to the right. So for example, if you notice here, at -1, right, it's going to be the value of -2 because the x value shifts 1 unit to the right. This is the normal shift that all graphs shift. This is going to be a horizontal shift. So in other words, this graph f of x equals to 2 to the x minus 1 is going to be this very same graph, but every value shifts 1 unit to the right. Everything. You see, for example, again, when it's -1, when it's -1 here, it's going to be 1/4, right? It's going to be like from -2 goes to -1. Then from -1 it goes to 0, right? Which will have the same y value, and so forth. Okay, but let me show you another example. And I apologize that I didn't graph that graph there. But here, guys, we have 2 to a negative x. This becomes 1/2 to the x power. And I showed these rules, I believe, in week number 5, I believe, where you have a negative exponent, all you do is do the reciprocal and make it positive. So this graph here, g of x 2 to a negative x, is the same thing as 1/2 to the x power. So again, if we plug in the same values for x from -3 to 3, these are the values for y. Okay. You see, if we plug in -3, it's going to give us 1/8. It's going to give us, we flip it, it's going to give us 8. There's my 8 right there. Then when I plug in -2, right, I repeat the process. When I plug in -2, let's go here. When I plug in -2, it's going to give us 4. When I plug in -1, it's going to give us 2, and so forth. So this is my graph. This is called an exponential decay because it starts high and it's going low. So again, when x is -3, my y will be 8. When x is -2, if you follow the arrow, my y will be 4. If x is -1, it's going to give us 2. When it's 0, it's going to give us 1. And then when it's 1, it's going to give us 1/2. And eventually, guys, as the numbers get larger for the x values, it's going to get closer and closer to 0. Okay, that's what it's going to be. When it's 2, it's going to be 1/4. When it's 3, it's going to be 1/8, and so forth. Okay, so this is a graph of g of x equals 2 to a negative x. This is called a decay problem or exponential decrease. Okay, now how do you apply exponential functions in real life? This is example number 4 here. The assets in billions of dollars for a Prudential Financial Incorporated can be approximated by the function ax equals to 315 e to the 0.056x. Okay, now, here, what we do here, let me see here real quick. We're going to plug in, for A part, If it says for x equals 7 corresponds to the year 2007, then the year 2000, it will be x equals to 0. And then x equals to 12 will correspond to the year 2012. So all we're doing for A is we're going to evaluate it at 0. So we're going to evaluate A of 0, which means I'm going to plug in a 0 for every x in the function, which will be right there where the x is. So it's going to be 315, the function, to the power of 0.056 times 0. It's going to give us 315. But since it's in billions of dollars, it's going to be $315 billion. Okay, this is good to know. The 315 is called the initial value because the time is 0. This will be crucial for the next example that I'm going to cover. But in the meantime, let's do B. So for B, we're going to evaluate it at 12, which means I'm going to plug in 12 for every x in the function. So it's going to be 315 e to the 0.056 times 12. All you do is put it in the calculator. And this is your result, 616.8171575. Let's round it out to the nearest tenth. So it's going to be 616.8 billion. That's the result for B. Okay, now this is number 5 here. It says here, a deadly virus has infected the world. At the end of January, there were 2 cases, and by the end of April, the cases had grown to 128. Find the model of the form f of t equals to y naught b to the t power, with t equals 0 corresponding to the end of the month of January. If the trend continues, how many people will be infected by the end of the year? So this type of problem, guys, is a 2-part problem. 2 parts. The first part, you have to find the function in the form f of t equals to y naught b to the t power. Okay, now this actually, I got this problem. Actually, when the coronavirus was barely here in the U.S., I believe at the end of January there were 2 cases. I believe in Washington. So I use this example to let the students know or how math is related in the real life. So this is a good example because it actually did happen. So now, what's my solution then? Here we go, guys. Need to find y naught and b, and then plug them in, and then that'll be my formula. So here's what we have to know. Y naught is the amount present at time equals 0. Remember in the previous example that I told you guys that when that y naught or the initial value is when t equals 0. So y naught is my initial value. Okay. Since t equals 0 corresponds to the end of January, then my y naught, which my initial value will be 2 because it started with 2 cases here on here at the problem says at the end of January there were 2 cases. So my y naught equals to 2. Then T1 corresponds to the end of February. T2 corresponds to the end of March. We have to go to the end of April, right? So we need to go on more. T equals 3 corresponds to the end of April. So by April, there were 128 cases. Okay. So I like to do this example like this, guys, like t equals 0 corresponds to the end of January and so forth, February and March, because this way we know that we have to find another point. So our next point is going to be 3 and 128. Okay. You see, when the time was 3, it was 128. So I'm going to use this and what we know, which was the initial value 2, and plug into the formula, guys, to solve for B. Okay, this is my y value, right? My y equals to y naught b to the t power. Here my t is 3 and my y is 128. And my initial value was 2. So all we do here, guys, is divide both sides by 2. So it's going to give us 64 equals to b to the third power. Now we're going to raise both sides to the power of 1/3 to cancel the 3 as the exponent. Here we apply the exponential power rule. When you have a power to a power, you multiply the powers. So 3 times 1/3 will just give us 1. That's why, and 64 to the 1/3 power will give us 4. So my b is equal to 4. So I found my y naught and I found my b. So we plug them into the formula. right? There's my y naught is 2 and my b is 4. Okay, now this is the first part of the problem here, right? This is part A. Now part B, on the second part, from January to December is 11 months. So we're going to evaluate f of 11, which means I'm going to plug in 11 where the t is on the function. And now we do is plug into the calculator. So it's going to give us, let's see here, 800. Let me see, 1, 2, 3. It's going to give us 8,388,608 people will be infected by the end of the year. In reality, guys, but when the coronavirus did strike, there was a lot of intervention. For example, there was or the 6 feet rule, right? That you can get closer to 6 feet to another person, and also there were masks. So all that were intervention. That's why there weren't that many cases. Why? Because there were intervention. This problem and this answer for B will be if there was no intervention. If it happened with nothing that we did, right? We just keep living our lives. Normally, this is how many people would have been infected, approximately that many people. And again, because the interventions, it was much less than that. Okay, but this is a good example of exponential function in a real life situation. Okay, now this next part that I'm going to cover is called solving exponential equations. Okay, here's a rule here. Let a be a positive real number with a cannot equal 1, because 1 to the n power will always give you 1. Okay, and then it says if a of u equals to a of v, then u must equal to v. In other words, if you have the same base, you let the exponents equal to each other. Okay, example. Here we have right, the base of the same, right, same base, so we can apply the rule. So we have the exponents must equal to each other, so x equals 5. But then every time you can have the same base, so you're gonna have to try to make them the same base. So for example, here we have 125 to the x equals to 5 to the 5th power. So not the same base. So I know that 125 equals to 5 cubed, right? Because 5 cubed is 5 times 5 times 5, which will give us 125. So I'm going to replace the 125 by the 5 cubed, right? And then here we're going to apply the exponential power rule. Apply the exponent power rule for the exponent. So a power to a power, we multiply the power. So it's going to give us 5 to the 3x equals to 5 to the 5th power. Now they're the same base, so now we can apply the rule. So 3x equals to 5. So the next step is all we do is divide by 3, and x equals to 5 over 3. Okay. And again, you can always check your work, the solution. If I plug in 5/3 for the x, it'll give us 125 to the 5/3 power. Right, you can plug into the calculator. So it's going to give you 3,125 on both sides, so we know that's the answer. And I believe, let me go back. I believe in week number 6 PowerPoint, I did tell you how to go from exponential to a radical and actually to solve it without the calculator. But in this case, it's easier to use a calculator, which will be 125 to the 5/3 power, which will give you 3,125, which will be equivalent to 5 to the 5th power. Okay, now this one here, right? They're not the same base. So let's see if 4 to a power will give me 32, right? So if we do 4 squared, it will give me 16, and 16 does not equal 32. Let's try 4 cubed. 4 cubed will give us 64. 64 is too much than 32. So that means that we have to find the same base between 4 and 32. Because 32 doesn't have a base with a 4. So that's why we have to find the same base with a 4 and the 32. So we know that the common basis between 4 and 32 is going to be 2, because 4 is equal to the 2nd power, and 32 is equal to 2 to the 5th power. So I'm going to replace the 4 with 2 squared. and we just bring the exponent down, and I'm going to replace the 32 with 2 to the 5th power. Okay. Now we can apply the exponent power rule, right? When you have a power to a power, we multiply the powers. You see, now we have the same base. So now we can apply the rule, which means we're going to let the exponents equal to each other. So we have 2 parentheses x minus 1 close parentheses equals 5. Now here we're going to distribute the 2. So it'll be 2x minus 2 equals 5. We're going to add 2 to both sides. 2x equals 7. Then we divide by 2. So my answer will be x equals to 7 over 2. That's my solution. And again, we can check our work. So let's check it. So I'm going to plug in 7 over 2 for the x's. So 7 over 2 minus 1 will give us 5 over 2. If you plug 4 to the power of 5 over 2, it's going to give us 32. So I know that's my solution. Okay. Now, the next examples that I'm going to do, we're going to be writing exponential equations into logarithmic equations and vice versa. So definition of logarithms to a base a. This is logarithm, and this is exponential. So these two are equivalent. This is the logarithmic form. This is the exponential form. Okay, so number 8, write each logarithmic equation into an exponential equation. You have log a base 9 of 81 equals 2. So we have to know what the x is, what the y is, and what the a is, right? So my a is going to be 9, right? My a is 9. My x will give us 81. My y is going to be 2. So then we go to the exponential function, right? So my a is 9, my y is 2, and my x is 81. So this is the exponent. This is the logarithmic form on the left, and this is my exponential form on the right. So this is how you can go back and forth from logarithmic equation to exponential and vice versa. For example, in example number 9, we're going to go from exponential to logarithmic equation. So again, we have to know what the a is, right? We have to know what the a, the x, and the y is. For example, the a is going to be 3. The y is going to be, the a is going to be 5, the y is going to be 3, and the x will give us 125. So we have y, my y is 3, so 3 equals to log a base a, my a is 5, and my x is 125. So 5 cubed equals to 125 is equivalent to 3 equals to log a base 5 to the 125. Or log a base 5 of 125 equals 3. Let me go back. Log a base 5 of 125 equals 3. So this is very straightforward, right? Going back and forth from logarithmic to exponential equations. All you have to know is the definition of logarithms, and how what y value is always the exponent of the base. The base on the log is a base here on the exponent, exponential function, and the x, right? The log of base ax, the x will be the x value over here on the right. So once you know what the a, the x, and the y is, all you do is plug them into the formula, guys, and that's it. These are very straightforward. Okay, now how do we graph logarithmic functions? You have to do it without a calculator, okay? So without a calculator, you have to convert the logarithm into an exponential function, okay? So example, I want you to graph y equals to log a base 2x, right? Remember that my a is my 2, and that's my y equals to x. So I have to, this is a function that I'm going to plug in the values now. But instead of plugging in the values for x, I'm going to plug them in for y. And I use the same values as before, right? -2 to 3. So again, if we plug in -2, it's going to give us 2 to a negative second power. It's going to give us 1/4. Right? So my x is 1/4. And if you notice, after we repeat the process, right, again like we did last time, when x is -1, right? I'm going to plug in the -1 for the y, and it's going to give us 1/2. Y is 0, x will be 1. Because all we're doing is plugging in, here for the value of y, and then we'll get the value for x. So when y is 1, 2 to the first power, right, x is 2. When y is 2, we plug in 2 there, right, x will give us 4. And when y is 3, we plug in the 3 for it'll be 2 to the third power. So my x will be 8. And here are the graphs of both the exponential and also the log. These are called inverse of each other. Okay, but I believe in 1324, they don't go over inverses as they do in the 1314 course. But anyway, the one in red is going to be the logarithmic equation of y equals log 2 base 2 to the x. This is how we graph the logarithmic equation. Okay. Now we're going to be expanding or condensing logarithmic expressions. For these are the properties that students must know. Okay. If you have log, these are called single logs. These are called expanded logs. For the single logs, right? If you have this is called a product rule. If you have the product, right, like x times y, you're going to expand it by using log of base ax plus log of base ay. And this is a quotient rule in a similar manner as a product, right? But if it's division, it's going to be a minus in between. Minus log of base ax minus log of base ay. And this is called the power property. If you notice, the power or the exponent goes to the front. You see it's right here in the front. Okay. And it also works the same thing for the natural log. These are the ln or the natural log. You see the same rule applies for all three. For the product, for the quotient, and for the power. Okay, now it says here, write each expression as a sum and or difference of a logarithms with all variables to the first degree. So here, guys, they give it to you guys in single log. You want to expand it. So what properties are present? We know we have the power, right? The power property and the product. So need to add 3 separate log terms, okay? Because it's going to be 1, 2, 3 terms. Log of 5, right? Plus log of x to the 4th, plus log of y cubed. Now the exponents must go to the front. You see, execute the power property, the exponent must go to the front. Right, so it's going to be, right, the exponent goes to the front. And also here on the log of, hey guys, if there's no base here, guys, it's base 10, right? So log of base 10y to the third, the exponent goes to the front. So this is the result. Okay, log of base 5. Log of base 10, 5 plus 4 log of base 10x plus 3 log of base 10y is equivalent to log of base 10, parentheses 5x to the 4th power, y to the 3rd power. This is called a single log. This is called expanded log. Okay, now let's try another one. Right, now here, right, which properties are present? So here, all properties are present. We got the product, we got the power, and we got the quotient. So all three are present. So why don't we start here, right? We're going to start with the quotient, right? It's going to be, because if it's division, like up here, like this rule here, division is going to be subtraction. So we start with that. Then, right, we're going to execute the product property. If you have multiplication, you're going to add them, separate them, and add them. We're going to have log of x plus log of y squared minus log of w. Now we're going to execute the power property. The exponent must go to the front. The exponent goes to the front. So this is in simplest form. Okay, you see all the variables are to the first degree. So again, this is the single log form. This is the expanded form. Okay, now let's try again. Let's do one more example. Now we're going the other way, right? Now let's expand it. You want to put it as a single log. Okay. So what properties are present? If we notice, right, we have the quotient property because we have subtraction. If it's subtraction, it's going to be the quotient property. If you have a coefficient in the front, it's also the power property because the coefficient must go to the top, right? Like the number in front goes to the top as an exponent, like it did here on rule number 3 there. So we start off, right? Execute the power property. The 2 must go to the front, right? The 2 goes to the top as an exponent. Then we're going to execute the quotient property. Subtract, right, because we have the quotient. So here's where we write it as a single log. So it's going to be the x plus 7 squared over x plus 3. This is my solution, guys, here, right? We went from expanded to a single log. Okay, now we're going to be solving logarithmic equations. So if we notice, we're going to take the natural log of both sides, because this right here we cannot execute. We cannot put them as the same base. Whenever that occurs, all you do is take the ln of both sides, right? You bring down the x by taking the ln of both sides. So by the rule, when you have the ln of a number to the power goes to the front. Okay. Now we can divide both sides by the ln of 6. And then we use a calculator, and this should be your result, right? So most of the time, I want you to run it out to 4 places. So the answer should be, or it is, 2.3869. Okay, now this is very important, guys. The ln of 72 or the ln of 6, guys, is actually a number. You cannot separate them. That's a misconception that students have. They try to divide by the ln. You cannot do that. You have to, because it has to be the ln of a number. That's a number, actual value. So like I put here on the note, very important. The ln of a number is an actual value. Cannot separate them. So please do not make that mistake. Okay, now solve, right? So before you use this property, it says here, let u, v, and a be positive real numbers, with a cannot equal to 1. If log of base au equals to log of base av, then u equals to v. But for you to apply this property, you have to have a single log on both sides of the equal sign. So the one on the right, I have to put it as a single log. So we're going to use the quotient rule. Right? The quotient, if it's subtraction, is going to be the quotient rule. Now, right now we have the same log on both sides, right? With the same base. If there's no base, the base is 10. So now we apply the rule, and we let the values of the log be equal to each other. So x equals to x plus 3 over x minus 1. Now here we're going to cross multiply. So x times x minus 1 equals to x plus 3. Distribute the x. So it's going to give us x squared minus x equals to x plus 3. We're going to let it equal to 0. The right side, so we're going to subtract minus x and minus 3 to both sides. So it's going to give us x squared minus 2x minus 3 equals 0. Now we got a factor. So when you factor, right, I believe this is a PowerPoint that I presented. I believe it was week 3. If you guys don't know how to factor, use that PowerPoint that I did, and hopefully it's going to help you to know how to factor. So anyway, x squared minus 2x minus 3 is equivalent in the factor form of x minus 3 times x plus 1. Now we let both binomials equals to 0. So we have x minus 3 equals 0, or x plus 1 equals 0. So x equals to positive 3. or x equals to -1. Now we get to check the answers. Okay, one thing that you should know, guys, is that the logs cannot have a negative number. So when x equals -1, right, and we plug in -1 for the x, and we put that in the calculator, it's going to give us error or undefined. You see, it's going to give us something not defined. So this is not a solution, which means -1 is not a solution. Now, if we plug in 3 for every x, well, we have log of 3 equals to log of 6 minus log of 2. Here we can just actually use a calculator, right? So this will give us the answers for both sides. But you can do it without the calculator. On the right side, right, we can apply the quotient property, but you're going to put it as a single log. So it's going to give us log of 6 divided by 2, which will give us log of 3. So log of 3 equals to log of 3. So these are equivalent. So the solution is 3. Okay, now this is another rule here. If a and u are positive real numbers with a cannot equal 1, then a raised to the power of log of base au equals to u. So in other words, I want to cancel the log of 4, right? I don't want that there. So I'm going to raise, like it says here, let the expression on both sides of the equal sign be the exponent. So in other words, this is going to be my exponent. So since it's base 4, I'm going to put a big 4, and this becomes your exponent, but on both sides. Now we can apply the rule. So this means that the 4 raised to the log of base 4, that's equal to 1. So this becomes x plus 6 equals to 4 squared. Now 4 squared is going to give us 16. Now we solve for x, right? Since we only have the x to the first power, I'm going to subtract 6 from both sides. So we have 5x equals 10. We divide both sides by 5, so x equals 2. And again, you can always check the solution. So I'm going to plug in 2 for the x, right? Because x equals to 2, so I'll plug in 2 there. So we have 5 times 10, so that will give us a log of base 4 to the 16th power. And if you use a change of base of log of base 4 of 16, it's going to give you 2. Or you can change the 16 to 4 squared. Then by rule, the exponent goes to the front, which will be 2. And log of base 4 of 4 is equal to 1. So in other words, you can use the change of base to plug in the calculator or do it by hand, but the result equals 2, which means that 2 is the correct answer. Okay. That's it, guys, for chapter 4. Now comes chapter 5, which is a simple interest 5.1. I believe I did one problem from each section. Okay, this is number 17. Gabriel invested his summer earnings of $3,000 in a savings account for college. The account pays 1.5 simple interest. What will be the value of the account after 2 years, and how much interest did he earn? So this is a formula for simple interest, right? So like I tell my students, you put every variable here on the left, right, vertically, and you're going to extract the information from what's given and put it on the correct variable. So for example, here on this one, number 17, what are we looking for? Okay, it says here, Gabriel invested his summer earnings of $3,000. This is what Gabriel invested, which was the present value. We're looking for the value of the account after 2 years, so we're looking for the future value. So now we're going to extract the 1.5% as the interest rate, which will be 0.015, and the time will be 2. So all we do is plug into the formula, right? My PV is 3,000. 1 plus 0.015 times 2, so it's going to give us 3090, 3,090. So in other words, then to find the interest, we're going to subtract the present value, which was a 3,000 minus the future value. So it'll be 3090 minus 3,000 is going to give us 90. So the future value, guys, after 2 years is going to be $3,090, and the interest earned was $90. So this is the answer for part A, and the 90 will be the answer for part B. Okay, now this is compound interest. This is 5.2. Here it tells you what every variable means, guys. The AV stands for the future or maturity value. I call it the future value. The PV is called the principal or present value. The R is the interest rate per period, converted to decimal. The M is the number of compounding periods per year. The T is number of years and the number of years. The I will be the R divided by M, which is the interest rate per period. And the N is equal to M times T, which is the total number of compounded periods. And here is the key value or the key word for M. If it says yearly or annually, the M is equal to 1. Bi-yearly or semi-annually, M is equal to 2. Quarterly, M is 4. Monthly, M is 12. Weekly, M is 52. And daily is going to be 360 or 365. If the book doesn't say to use 360, well, then you just use 365. And compounded continuous is a different formula, which would be the future value equals to present value, e to the power of RT. Okay, now, compound interest can be used to invest a certain amount of money without depositing additional money. So let's do an example here. Say this is number 18. You deposit $9,000 in an account at your bank that pays 2.5% interest semi-annually. How much money will be in your account after 10 years? And how much interest did you earn? This is my formula, right? So there's 7 things that you have to keep account of, right? Here are my 7 things. So here, guys, we're looking for the future value. So the 9,000 is the present value that you put in. My R will be 2.5%, which will be 0.025. My M, right, is compounded semi-annually, which will be 2. My T will be 10. Now my I is my R divided by M, which will be 0.025 divided by 2, which will be 0.0125. My N is M times T, which will be 2 times 10, which give us 20. Now all we do is plug into the formula, right? There's my present value, the 9,000. There's my I is 0.0125, and my N will be 20. Now all we do is plug into the calculator just the way it is. And this is your result. $11,538.34 because we round out to our nearest penny. So 0.335 rounds out to 0.34. So it's going to be $11,538.34. Okay, now how much interest did you earn? So here, so for the interest earned is going to be the future value of what we just got minus the present value of what you invested. So the future value was $11,538.34, and the present value of what you invested at the beginning was 9,000. So you subtract it. Now this is how much money you got in interest, which is $2,538.34. This is the answer for the second part. Okay. Okay, now I believe we have 2 more problems to do. This is from 5.3. 5.3 is used to find funds in the future, right? That's why it's called the future value of an ordinary annuity. This is good to set up like an account to have a certain amount of money in the account after so many years, but you have to put equal payments every so often. Or, for example, in this case, right, it says at the end of each quarter, a 50-year-old woman puts $1,200 in their retirement account that pays 7.2% compounded quarterly. When she reaches 60, what will be the value in the account? And how much interest will she earn? So again, we're looking for the future value. So the payments are $1,200. My interest rate is going to be 7.2%, which will be 0.072. My M, right, compounded quarterly. So quarterly means 4. And my T, right? The T is not given, right? But what is given is when the woman opens the account, right? And when the woman, she wants to get the account after she's 60, so from 50 to 60 is going to be 10 years. So for my I will be R divided by M, 0.072 divided by 4 will give us 0.018. My N will be M times T, will be 4 times 10, will give us 40. Plug them into the formula, right? And then use a calculator. And here's how to use a calculator without clearing or stopping. One steady flow until you reach the answer. So you're going to put what's here, guys, on the numerator, the parentheses, 1 plus 0.018, close parentheses to the power of 40 minus 1. And this is a value that you should see in your calculator. Okay, after you do that, you're going to hit the division key. Right, you're going to hit that division key. And divided by, you should see answer right, divided by something here. Answer, this what you should see on the screen, answer with a division symbol there. Then you're going to enter the 0.018. After you do that, you should see something like 57.85111.879 on the screen. Now you're going to press the multiplication key, and then you're going to enter it, right? You're going to multiply that by the 1200. You enter the 1200, so you should get something like $69,421.34. Okay, that's how much it was in 10 years. So how much of it was interest? How much money did you invest? So how many payments were there? There were 40 payments, right? 40 times 1200, because that was the amount of the payments that the woman put in every 4 months. So we multiply those, so it's going to give us 48,000. But the woman received 69,421.34 cents, right? So we subtract the 48,000 minus what we got for the future value. It should give us something like $21,421.34. So this is the amount that the old woman got in interest. Okay, which is not bad, right? In 10 years to get that much money for free or in interest because you invested the 1,200 of equal payments for 10 years, 4 times a year. This is your solutions here, guys. Now, number 20 is actually one of the most important investments that someone's going to make. So I like to use this. The opportunity when I teach this section is to actually to relate it to a real situation. And I believe I got this problem from a student. He said that when he starts making good money, when he gets a job and all that he wants to buy a house that's worth about $325,000. And let's say that the interest rate is 3.9%. How much will the monthly payments be? And how much interest would that person end up paying at the end? So again, I got this scenario from a student, right? That's the house that he wants. Let's see if the payments, how much the payments are. So now, right? So now we're looking for here, guys. We're looking for the payments, correct? So we're looking for the payments. This money here, the 325, is a present value. That's the money that you're going to borrow from the bank. Now the interest rate is 3.9%, will be 0.039. The M is going to be 12, right? Because for real big investments like houses or cars, there's always monthly payments. So the M will be 12. The T is for 30 years. So let's find the I. The I is R divided by M, will give us 0.00325. And the N will be the M, the 12 times the 30, which will give us 360. Just plug them into the formula. And again, guys, I'm going to use the inverse to find the payment, okay? By that, I mean, here's how you plug into the calculator. You're going to plug in the numerator just the way it is. 1 minus parentheses 1 plus 0.00325, close parentheses, to the power of negative 360. So this is what you should see on the screen. 0.68904369001. Then you're going to hit the division key. After you do that, this is what the screen should look like. then you're going to enter 0.00325. You're going to hit enter. So this is what you should see on the screen. Now here, guys, right, this whole right side is equal to 212.0134431 times the payment, right? So here's where we use the inverse key. You're going to press on the inverse key. That's a key on your calculator. So you're going to press that, right? This is what you should see on the screen. When you see that, you're going to enter the 325,000. And that's what we get. So we get $1,532.92. So those are your payments. Okay, but now let's see how much money that you actually put into the house. The house was worth $325,000. You made 360 payments at $1,532.92 every month. So we're going to multiply those up. So this is how much money you actually paid for the house. $551,851.20. Right? That's how much you paid for the house. Now, how much interest did you pay? So I subtract the loan amount, which was a 325, from the 551,851, and we should get something like a little bit over of $250,000, $226,851. This is how much money you paid extra. Okay, now I always tell my students that to always pay a little bit extra every month, because you can pay the house actually in less than 30 years if you keep paying extra payments or extra funds into the principal. That way, whatever extra you put in extra every month goes straight to the principal, and the house will be paid in less than those 30 years or less than 360 months. Hey guys, I hope this PowerPoint was helpful to you guys. I did do a question from, I did cover every section on the exam. For example, I give students 10 questions on an exam for 50 minutes. And if it was a class of an hour and 20 minutes, more likely the instructors will give about 15 to 20 questions. It depends on the time. But I hope you guys enjoy this PowerPoint and you guys can use it as a learning tool for your exam for this week. Okay, let me go back. Do you guys have any questions? If you do, get in the mic or put it in the chat and I can answer your questions. If not, well, thank you very much again for joining my Happy Math Hour, and I'll see you guys next week. In 2 weeks.